Okay, so maybe we should start since we're a little bit pushed for time. Today we have the nice topic of unfolding in high-energy physics. We've got various speakers, and since we have so many speakers and so many slides, maybe we should just jump straight into it. To start us off, we have Tim and Adye. So if you could, do you want to share your own slides? Tim,
shall I share my slides? Yeah.
That would be ideal, I think.
Okay. Do you see those?
Yes.
I see them. Yes.
Good. Okay. So I'll give a sort of a general kind of software type view of the RooUnfold package without going into any of the details of the unfolding algorithms, since I think the scope of most of this, well, I suppose I was asked to concentrate on that those aspects, but there are in the backup some details for each of the algorithms under study that are implemented. So on page 2. Sort of overview of RooUnfold. Its purpose is to provide a framework for testing and using different binned unfolding methods, and the purpose is to maintain as consistent a view of each method so that people only need to code up one set of calls for their particular use case, and then can switch and compare the different algorithms. So the algorithms that are implemented are the first one was the iterative Bayes method, which was originally described by D'Agostini in a paper from 1995. But this RooUnfold also has a fairly major fix for the error calculation that wasn't included in D'Agostini's original description, and I suspect may even have prompted him to move to a different method that does the errors better, but actually D'Agostini's original method with the corrected errors does seem to work well. And in fact, this method seems to be used by probably the majority of RooUnfold users. And so sometimes I suspect people confuse the term RooUnfold to be just the iterative Bayes method, but in fact it is for the idea is that it's a framework for many different methods. So the next one that I mention here is was added quite recently by Chris Meyer, our next speaker, is the iterative dynamically stabilized unfolding that Bogdan Milescu has described in 2011. This is now implemented as as another algorithm for within RooUnfold. Then thirdly, the singular value decomposition method. So it's basically performs a singular value decomposition on the response matrix and then removes high frequency terms to perform the regularization that was originally described in 1995, but and implemented by Kirsten Tachman and others. So this method is available separately also already in the TSVD Unfold root class, but the RooUnfold has a small improvement to that in a private version within the RooUnfold code. But basically, the idea is that once that it can interface directly to the root version once that is implemented within root. And then also another one is regularized least square fit, which is implemented in the T-Unfold class. This is used directly from the class within root, but with an interface again, so that, as with all these methods, they can be used in very similar ways. That's implemented and designed by Stefan Schmidt. And then a couple of methods which are basically for comparison of kind of simpler methods, one being just an unregularized matrix inversion with removing completely singular values, and also the bin by bin with correction factors, which you don't need an unfolding package to implement, but allows a simple comparison to see whether you need to be using unfolding in the first place. On top of the of various algorithms, RooUnfold provides common features interfaces for these different algorithms, but also various convenient methods for providing the inputs in different forms. So the response matrix can be given as histograms or matrices or filled directly. You can specify these as 1, 2D or 3D truth or measured distributions, and use different binning in measured and truth. I'll come on to these in a little more detail in later slides. It also supports for inefficiency and fakes, and this is sort of within the interface layer between RooUnfold and the algorithms, so it works even when the algorithms don't support those, and can take care of propagation of errors either via linear error propagation or automatically using toys. And the package also provides some simple examples for use in C++ and Python. The RooUnfold itself is implemented in C++, but you can call it via the PyRoot interface. And there's also an extensive test suite for comparing the different algorithms using various different simple toy Monte Carlo distributions. So to see, so that can be used and it can test any of the other features that I mentioned above, and could all be done from the command line. There's some rather old documentation and instructions, and download the latest version and references on the web page that's mentioned here. A sort of a rather schematic view of how this works is that you give as input in the top left these the training truth and then the measured truth and a response matrix as input to the RooUnfold response object, or alternatively you can train it using use it directly using calls to the RooUnfold response object. The response object and the input measured data are then used as input to the RooUnfold class, which is inherited from all the various algorithms that are implemented in RooUnfold. And then as output, you get an unfolded distribution, either as a histogram or as a vector, and with either errors or a matrix, a covariance matrix of all the errors. One other feature which is useful is that you can also save the response matrix to disk, allowing you to, so that you can basically you do the training in one step, and then separately you can do the unfolding as a separate step. And this was a kind of nice thing that came for free from the fact that RooUnfold is using root objects. Of course, this was more of a special feature when RooUnfold was new than it is nowadays. So just as an example of how this unfolding looks like, this is an example from the test suite. So imagine that you're sort of training on a sample here with you have in green a PDF distribution, PDF of the function. In this case, it's just a Gaussian with a flat background, which is then from that is generated some toy Monte Carlo in the blue histogram, and that is then smeared with a Gaussian smearing function, some systematic translation applied, and some variable inefficiency, so that you have you can see that on the left you lose less of the signal than on the right, and so the translation from the truth to the measured in the training is then used to fill the response matrix, this RooUnfold response object, which is then used for the unfolding at the bottom, where again we start off now with a rather more complicated function. This is quite a challenging one because it's got quite a lot of structure, a double bright Wigner with a flat background, and so the result of the same smearing, translation, and inefficiencies then applied to the truth distribution gives you in red the measured distribution that would be the result of your experiment, for example, and then the unfolding undoes that effect to give you the black points, and you can see the black points mostly line up quite well with the truth. There are a few places where they're kind of several sigma away from the truth. That's primarily because this is a challenging example where there's a lot of structure, and if you can then adjust this by changing the regularization. So just to then discuss a few of the particular things that I think are used quite a lot in unfolding, and so should probably of interest to if people are thinking about implementing something different. I think these are all things that should be considered. One is that is in particular 1 or 2D truth or measured distributions. So in RooUnfold, these are internally unpacked into 1D distributions, and there's a problem with the two methods that use smoothing between neighboring bins, because they have to do the smoothing. They have to kind of have knowledge about which bins are neighboring to each bin. So in T-unfold, there's a multi-dimensional smoothing that's automatically selected. This doesn't work or is not implemented for the SVD method. So 2D or 3D doesn't work for the SVD method, but it works for all the others. The other methods that don't require smoothing, and so are a sort of they're more akin to a matrix inversion without considering the structure of individual bins. So can handle this directly once the distributions have been unpacked into a 1D distribution. There is, though, one thing a warning, because several people have hit this, that you should choose your binning with care. With a 2D distribution, that means the response matrix has n to the fourth bins. If you've got a n by n 2D distribution, then you've got n to the fourth response matrix bins, which can require a lot of Monte Carlo for reasonable statistics, and in some cases even a lot of memory just to hold the response matrix in RAM. So that has to be carefully, if you're doing a 2D or even a 3D distribution, you have to have it only really works well if you have a limited number of bins. Another thing that unfolding, as in particular in the example I showed you before, is sort of most naturally thought of as the same number of bins for the truth and measured distribution, but actually that's not necessarily the best way to implement it or to use it. And in fact, in particular, T-unfold requires that the number of measured bins is equal to or larger than the number of truth bins, but the other methods would allow different numbers of measured and truth bins. But in T-unfold, it actually claims that the best results, if the number of measured bins is greater than the number of truth bins, for example, twice the number of truth bins. This is in general a common recommendation from unfolding experts, but perhaps is most relevant for these types of algorithms where you have an explicit regularization. And this is an implicit, I think the reason for this is that this is an implicit additional regularization, because it, by merging two bins, you're kind of you're smoothing, you're performing an implicit smoothing between those bins by going from the truth to the measured distribution. The SVD and the bin-by-bin methods don't really handle the number of measured and truth if they're expected to be the same. So the response matrix is supposed to be a square matrix. It is possible the RooUnfold use of the CAT does actually try and correct for this, but it won't do a very good job because the method itself doesn't handle this case very well. The other case which sort of on top of some of the algorithms is handling inefficiencies and fakes. So as well as migration between bins, we could also model what's called either misses or inefficiencies or effectless causes. So these are truth entries with no corresponding measurement. Or alternatively, I mean, the other side of the coin is are fakes or backgrounds or causeless effects. These are measurements with no corresponding truth entry. Now, RooUnfold allows misses and fakes to be specified when filling the response matrix. And, just to show you, sorry, this is the plot here shows similar example to what we saw before, but also in addition, the fake distribution in yellow can also be corrected, can be taken into account for, and can then reconstruct the unfolded distribution with the black points, and again still agrees quite well with the original truth distribution. The way that RooUnfold implements this, it can either be specified, you can specify the misses and fakes with the response matrix, or infer it from the 1D truth or measured histograms given when you're creating the 2D response matrix. So it's basically based on the relative normalization of the truth and measured histograms relative to the response matrix. gives you you can then infer the efficiencies or fakes, or you can specify them directly when you create the response matrix. The way that it's handled by each unfolding method is a bit different, and this is it's not very consistent between the different methods. For the iterative Bayes method, or I should say, generally the misses are treated as a sort of multiplicative efficiency, and the fakes as a sort of additive background. So the way this is handled for the iterative Bayes method, for example, that misses are the response matrix is scaled by the efficiency of each truth bin, whereas the fakes are handled as an extra truth bin for the background that's added to the response bin. So it's basically, if you start off with a response matrix that's n by n, then it will be n by n plus 1 in the with one extra truth bin. Alternatively, if one can, if people don't like the way this is handled automatically within RooUnfold, it's always possible to do this by hand outside of RooUnfold, and then just pass RooUnfold without give the response matrix without including the misses and fakes, and then correct for it afterwards. So this is the RooUnfold's handling of this is convenient, but may not be the way you would want to handle this. Maybe this is something that could be improved with a more systematic treatment of misses and fakes for the different algorithms.
Tim?
Yes.
Hi, this is Kyle. So I am appreciating very much the talk. I'm also just noting a little bit the time, just so we have to be a little bit careful about time for the rest of if we're going to get through everything.
Yeah, don't worry. Most of my talk is back up, so I'm.
Oh, okay, I see. Sorry.
I'm about 4 slides from the end.
Okay, great. Okay,
so,
never mind.
Yes, but I'll try and go. So RooUnfold then can also handle the errors on the unfolded distributions. We have you can either just get the histogram bin errors, get them out from the, or extract the full covariance matrix as a T matrix D, and as input, you can input either the measurement errors with either default root n, or passed with the histogram, or set an input covariance matrix, and can also take care of the response matrix with the include systematics call. So error propagation can either be done by propagating the errors through the transforms, which is kind of assumes everything is roughly linear, or by internally generated toys. It's automatically calculated. And the plot here shows for the Bayes method, comparing the histogram being the error propagation, or the toys with being the points, for different numbers of iterations, and you can see that the two are well reproduced. The two methods well reproduce each other. So RooUnfold, the history is it started in 2005 with the Bayes and SVD unfolding methods. I'll go through quite quickly here, but I think one thing that's worth highlighting is from 2010 to 2011 in particular, the Helmholtz Alliance unfolding project discussed many of the unfolding, kind of general unfolding techniques, and there was a lot of development, and it prompted a lot of development in RooUnfold, and still RooUnfold is using the DAISY SVN server, which was set up for as part of this this effort, very useful effort. So then we was added the TUnfold interface, error calculations using toys, and all in 2010, and then in 2011 the Bayes method was re-implemented using matrix methods, and fixing the error propagation that I mentioned was a problem with the original implementation of the Bayes method. So the last release version was 1.1.1, which and then we added propagation of response matrix errors since that in the SVN version. It's been included in the Atlas root core releases, and most recently Chris has added the IDS unfolding algorithm. I just did a sort of a check of the citations for the RooUnfold physStat note, and it seems this has been used in, or at least referred to, from 110 papers, published papers, and 158 other types of papers. So I don't know if that's that's probably a measure of a rough measure of how widely it's used. I'm sure not everybody's referring to this particular note, and also some people, probably some of the references are from people who said we thought about this and didn't use it. So but it's maybe a rough measurement. And I've been contacted by many people with questions and suggestions, and some bug fixes from particle physics, astrophysics, and nuclear physics. So it seems to be quite widely used. I just very quickly here just mention the status. The problem here is that RooUnfold was last updated, the last version was now 6 years ago. It has been continued to developed in SVN, and I'd now recommend that anyone who picks it up uses the version from SVN. This is documented on the web page, and I think my next job, which I'll just come on to here, is to this is just listing the changes in the development version. I think I've discussed all these before. Just to mention that it can be used with root, with the old root 5 sint or cling, or the compiled C++ compilation, and pyroot, and so these are all different methods of that can be using RooUnfold, that you can run the examples from. So to the I guess the main thing for the future is I've collected many interesting and useful suggestions for improvements. So interfaces with new algorithms, new tests, more convenient ways of using it, and API improvements. But I've had very little time to work on unfolding, which has always been a spare time job. Unfortunately, other spare time jobs have taken precedence for the last few years. But I've, in the backup, have put a very kind of raw list of various things that I've noted down over the last few years. But the first priority is, I'm really hoping to get to this in the next few weeks or months. So the warning is that I've said that before, and so far I haven't managed to. But the first thing is to make a new release based on the development version, so that the documentation then can refer to the correct version, to the version that you would expect to download, and update and improve the documentation, especially the setup and examples with root 6 and cling and pyroot. So because the original version, I think the current documentation is still referring to root 5.24, which is some years old, many years old. and then various other things need documenting. And I always have the plan, and has been agreed in principle, but I'd like to submit this also for inclusion into Root, so that it can migrate with improvements to Root. So in summary, RooUnfold is a widely used framework for accessing different unfolding algorithms. In particular, it implements D'Agostini's iterative Bayes method, but it also implements many others in parallel. And so just because the Bayes method is used most doesn't mean it's the best or the most or should be the most widely used. They can all be used and compared. And it implements many common requirements: multi-dimensional binning, inefficiencies and fakes, error calculations using different methods, and algorithm tests using toy Monte Carlo. One big thing that's missing is a common framework or recommendations for evaluating algorithms and their configuration for any specific physics distributions. I think I hope that the next talk will discuss this in some detail.
Great, thank you, Tim. That's excellent. We could have maybe some burning questions, but for time, we shouldn't spend too long. Could I ask quickly, in terms of if you wanted to if people want to propagate uncertainties, there's a you told me a little bit about how it works, but if you have some notion of breakdown between different kinds of systematics and things like that, you would basically use it. It's not providing any utility for that. You would basically just propagate each uncertainty individually and then sort of figure out what to do with it. Is that right?
Yes, that's right. Yes, mostly the assumption is that you have a total uncertainty, and then you can propagate the errors using either of the two methods. I sort of misleadingly in the code, the systematics are the term includes systematics is a method. Is the name of a method, but it actually means just include the systematics from the response matrix. So include uncertainties from the response matrix in the overall unfolding, because there's two sources. You can either have the errors coming in from the measurements or the errors coming in from the uncertainties on the response matrix. But splitting those up more detail if you have individual sources of one or other of those, you can't. You have to basically rerun RooUnfold with the different uncertainties included. Is that what you meant?
Yeah, I think that's good. I'm sure in more detail would take more and more time, but that's gets across the idea. Thank you.
This is Science here. One of the procedures you described was bin-by-bin correction. Does that come with a RooUnfold warning that it's not a very good method?
Well, in all the documentation, yes, I say it's not a very good method. I think the idea I've always sort of advertised that as a try this to see whether you need to use RooUnfold. Where it will work fine is if you have no bin migrations or very small bin migrations, then the bin-by-bin method is no worse than the other methods and probably simpler.
I think in general we want to dissuade people from using it.
Yeah, well, I guess it's the first thing people always try, and but I guess if you know that bin migrations are small, then maybe you don't need to think about using unfolding at all.
Is that okay? How about now? Can people hear us?
I can hear you.
Yes, I hear you. Yeah, we should go ahead and move on to Chris's talk.
Okay, great. I apologize in advance. I have a few deadlines tonight, so I will have to leave after my talk. But I looked ahead, and all the other talks look very interesting, and I'm sorry to miss the discussion. I also don't have too many public things to cite. As nice as it is to have this open discussion with Diana HEP, and I think it's a very nice place to have this type of discussion. I guess a lot of the things I've been working on are all internal to the Atlas collaboration, so there's not any hard examples, but I'll try to be as specific and useful as I can in any case. So there are many unfolding methods available, as we saw this nice talk by Tim. The bin by bin. I took a peek at the next talk, and I changed Bayesian unfolding to D'Agostoni iterative. I'll let the next speaker mention that a bit more, though. SVD, IDS, matrix method, you name it. There are many methods, and they all have different benefits. So bin by bin, I'm not trying to open a bag of worms here. It's simple, although it is often avoided due to larger biases and other issues. With matrix inversion, this is minimally biased, but often results in wild oscillations and fluctuations. And then, of course, you get into the regularized methods, which seem to be what people enjoy using the most, or they give the best results often. So SVD, D'Agostoni, iterative, IDS. These avoid the oscillating results while keeping a minimal bias. It's somehow a compromise. So when choosing these, it's important to compare what method you want to use. And this is, of course, important, and it's different for whatever analysis you're working on. Every analysis isn't served the same by some golden unfolding method. So in this talk, I'll talk about a few things to think about, at least, when making this comparison between unfolding methods. So what are the possible sources of unfolding bias? I don't think this is an exhaustive list, but perhaps some of the larger ones are Monte Carlo simulation doesn't perfectly describe the collected data. Of course, if it did, we wouldn't be measuring anything because we'd already know everything. So that there are shape uncertainties in Monte Carlo itself that we're using to try to correct back to our unfolded measurement. There's also the regularization procedure. For example, you can make constraints on the smoothness of the spectra in order to suppress these statistical fluctuations. But over-constraints can often lead to biases, so you want to avoid these. And then finally, there's large bin migrations, and they can amplify either of the biases above. If you don't have very many bin migrations, then you don't have much to worry about. So the larger they are, the more these two things tend to make a difference. So first, there's this general shape bias. In order to compare methods, it's nice to define a bias metric. And one way to do this is with a Monte Carlo simulation. So the idea is if you unfold a RICO or a reconstructed spectra where you know what the true spectra looks like, you can compare the unfolded RICO spectra to the true spectra. And if the same, then hey, you win. Now, one thing to point out is you want to avoid using identical Monte Carlo simulation, of course, that you use for migration matrix. I mean, this is somehow a trivial closure test, right? If you assume no bugs, then if you unfold your RICO spectra with what you derived it from and you get the true spectra, well, this is good, but it doesn't tell you much about the bias of the method. Presumably, data doesn't look like Monte Carlo, and this is why you need to find an uncertainty for it. So for a robust test, you need to consider different input and output pairs. So by input-output pairs here, I mean a different RICO spectra that are matched to true spectra that aren't necessarily, or definitely aren't, the same as the migration matrix that you're using in this unfolding. So one commonly used method is the in situ method, or I call it the in situ method. I'm not sure there's an official name. This is where you change the shape of the input Monte Carlo to better describe the data. So you can change the true shape by using some smooth function. You multiply every event, or if you have a migration matrix, you can multiply every truth bin by some smooth function and propagate this through to the reconstructed spectra. And you can kind of iterate over this process, either by informed guesses or just until you find something that works, until you find this modified reconstructed spectra that looks more like data. And in this case, you have a data-like reconstructed spectra with a matching truth spectrum. Okay? And this is different than, let's say, the nominal migration matrix. You can then unfold this data-like reconstructed spectra with the nominal migration matrix. And since you know what it should look like at the truth level, you can compare your unfolded version of this data-like spectra with the expected truth. And if there's any differences, then this is a bias. The difference in shape between what you're unfolding and the migration matrix, or just uncertainties in the method itself, over regularization, for example, will give you a different shape, and this is the bias. Now, you can define this bias in the same way with any input-output pair, any kind of RICO spectra matched to a truth spectra. You don't have to do it through matching new data. You can use other things. You can look at different Monte Carlo reweightings. For example, you can reweight a different kinematic distribution. If you are measuring a PT spectra and you know that the rapidity distribution is horribly mismodeled, you can reweight the rapidity distribution so that perhaps it looks more like data. And then after reweighting the rapidity distribution, look at in the same Monte Carlo sample where you kind of fix the shape of the rapidity, unfold the fixed PT shape, perhaps not fixed in itself, but fixed in the rapidity sense, and then compare with the expected Monte Carlo truth using the original migration matrix. So you often choose one that's going to be mismodeled. For example, if you're unfolding some kind of Higgs spectra back in the day, a few years ago before we had next to leading order parton shower predictions, you would fix the PT spectra and then unfold something like cos theta star. Now, you can also consider beyond the standard models and unfold them by your standard model simulation you're nominally using to unfold the data. So if you expect new physics somewhere, this will of course cause a difference in the shape, and just by the fact that you've generated this Monte Carlo simulation, you have the RICO spectra and the true spectra, you can compare one after unfolding to the other. So the important thing here is to choose the shape difference that is appropriate for your analysis. Now, I'm not trying to set up hard and fast rules here. It's very analysis dependent, but say you're measuring a precision standard model measurement where it's already fairly well constrained, but you want to increase the statistics, decrease, say, a jet energy scale on a dijet mass spectra. Perhaps the in situ method, where you're not necessarily expecting new physics, but the Monte Carlo might not completely describe the data, would be a good method to determine the bias here. Or if an alternative variable that's not modeled correctly, you could reweight by that and then use that method. On the other hand, if you have a spectra that might include new physics, if you're unfolding something like a dijet mass spectra and you want people to use this outside of the analysis to test for new physics, then perhaps you want to consider beyond the standard model reweightings that might include bumps or something like this. And the idea isn't necessarily to assign a bias uncertainty on this folding, that you can use the in situ method for that in most cases. But the idea is to consider a wide range of possibilities and then determine which unfolding method does the best. So you want a range of shape differences that you're going to unfold with your nominal method and then compute the bias for each of them. And it may be, let's say, a bit horribly large if you're considering some wild BSM model, but you then compare the different unfolding methods and see which one handles it the best. It's not necessarily that you have to have a super small bias uncertainty if you're using a BSM model. You just want to see which unfolding method does the best job here. You also have to consider the statistical uncertainty. The amount of regularization, which are in all of these popular unfolding methods, affects the statistical uncertainty. If you have a smoothness constraint or an iterative procedure, you can either blow up the statistical uncertainty or dramatically decrease it. You should consider realistic statistical uncertainty in your bias test. One way to do this, a very good way of doing this, is to throw pseudospectrum from a data-like reconstructed spectrum. So here you're taking your Monte Carlo at the RICO level that has a different shape, and you take the Poisson errors from the data that you're expecting, not the Monte Carlo uncertainty, but the data expected error, and then you just throw a bunch of toys. You get all of these pseudospectrum. You can then unfold each one and compare it with the true spectra, and you also can build a covariance matrix with each one of these to get the statistical uncertainty and all the correlations. Since we're dealing with migration matrix methods here, it's important to keep track of the covariance matrix. So one more slide which tries to kind of bring all of this together. The previous slides discussed how you can get this bias using various different shapes that may or may not be realistic, and getting the statistical uncertainty in this covariance matrix. So it's not necessarily obvious how to combine all this information, and I think it very much depends on the situation you're in. But a few general thoughts on the method that you choose. You can just kind of look at the the bias and try to minimize that without increasing the statistical uncertainty too much, and that's just a very basic check. You can try to be a bit better about it. You can require that the bias is, say, less than 10% of the statistical uncertainty in most bins. Another thing that you often think of is statistical uncertainty shouldn't increase or decrease too much, both in individual bins or in sums of bins. That's probably pointing at an over-regularization. Statistical correlations also need to be considered. Migration matrices, when they're moving events around, will introduce correlations between bins. So you can't just take the diagonal uncertainties and say, well, I see a huge increase in uncertainty. Maybe so, but if you count for the correlations, the anti-correlations mean that the total uncertainty didn't actually blow up. It's just you're moving events around in a way that, to keep account of that, some uncertainties went up and down, but the correlated uncertainties are about the same. So then you can build fancier ideas like taking the sum of the absolute bias and then dividing by the square root of the sum of the covariance matrix elements. This is the idea anyways, is to get at the absolute value of the bias. If you just sum the bias itself, let's say one bin had a bias up and the next bin had a bias down. On average, you'd have zero bias and you would learn nothing, even though your uncertainty does have, your measurement does have uncertainties on various different bins. So you can sum up the absolute bias and then account for that by saying you want that to be smaller or small relative to the total statistical uncertainty, where you at least try to take account of the correlations. So this combines the two ideas above a bit, and you can come up with a number of these variables that get at a similar idea as this. So in summary, I think I'm closing right in on 10 minutes or thereabouts. It's important to compare different unfolding methods. However, the choice is highly analysis dependent, and you should also, if you've chosen an unfolding method because it's doing better, of course, compare different regularizations for that same method, because that will also change things and try to choose the best one. You should consider a number of things when choosing them, but in general, the size of the unfolding bias. I've given you one way to find this bias, the change in the statistical uncertainty, as well as the resulting correlation between bins. So unfortunately, there is no central place that is, for example, in RooUnfold, but it would be great if, I don't necessarily have time in the next month or two, but at some point it would be great if all of this could be put somewhere, or everybody can use it just by default when they unfold. So.
Well, thank you very much. Is there time for some very quick questions before we move on to Mikael's talk?
Let me ask a question. If I'm looking at the definition of the biases and defining the bias metric on page number 4, as far as I understand, this is done after the binning, right? So if you define the bias matrix and the uncertainty after the binning, that means that your best unfolding implies that you should bin everything into one single bin, because you get the smallest bias and the best uncertainty for that. So it kind of defeats the whole purpose of this thing, right? Doesn't it?
I mean, you're saying that you would find the smallest bias if you use this method to determine your binning. But I guess I'm proposing that in this case you would have determined your binning in some other way, say using the resolution of the detector and expected statistical uncertainty. So you have a set binning, and then for that set binning you can compute the bias this way.
Okay, but you should realize that binning is actually equivalent to regularization, right? So you have certain cost in binning. So and the cost is twofold. One is you're losing information about the signal frequencies beyond whatever the Nyquist frequency of the bins. And the second is that, you basically get a biased matrix, biased folding matrix, right? So in a sense, in this whole idea of comparing methods of unfolding, I think the binning effects have to be included from the very beginning, and the idea of the information loss should be included from the very beginning. Because otherwise, you're getting into strange situations when your best unfolding method, implies that you should use single bin for everything.
I don't argue against that statement. It would be nice to include some of this stuff earlier. I don't think that you will get dramatically different results in many situations from including everything, but it's certainly something that can be looked at.
Yes, I think your list of biases on slide number 3 is basically missing one important source, which is exactly the one that Igor is pointing out. So basically, if you use large bins, then there is a bias which is caused by basically the shape of the spectrum inside of the bins, and basically if you're in the kind of the extreme case where you have just one large bin, or I guess let's say just a couple of very big bins, then that uncertainty or that bias actually becomes a major factor, and as it was pointed out, it definitely should be taken into account in these comparisons.
But if you've already chosen to set binning, let's say because if you went any narrower, you don't have enough events and the statistical uncertainty is too large, that bias should show up in the method described here, right? Because as you're changing the shape within reasonable ways, then you will find the bias because the migration matrix in this, let's say, non-optimal binning just doesn't behave very well, right? I mean, it certainly is a source of bias, but you're not necessarily underestimating it here.
Well, bins are just a way to split your event sample into non-overlapping, things, right? You could do this non-overlapping split by using different basis functions. Those don't have to be rectangular bins. Those could be, for example, Chebyshev polynomials or something else. So I think the question about the determination of optimal bin widths, or in general the determination of the optimal basis, should be a part of this whole discussion.
Yeah, so this is I think that it's an interesting discussion. Maybe we can come back to it after the talk. I'm not trying to, but let's don't get too carried away in this point before we get through the rest of the talk.
Yeah, so thanks again to Chris for sharing that with us. Mikael, you agreed to share your slides?
Yes, so let's see if this works. Can you see the slides? I think I just shared them. Can you confirm that you see the slides?
I don't see them yet, but okay, now I do. Yeah.
Okay, so it sounds like it's working. Okay, so so I'll be giving some ideas how, from my perspective, the current unfolding software could be improved. And then this is very much focused on the kind of the methodological and statistical side of things. So as you probably pointed out, I'm a statistician, but I've been working for many years now with the CMS Statistics Committee, especially on unfolding issues. And so a lot of this talk basically comes from that experience. So here on slide number 2 is kind of my one-slide introduction to what the current unfolding methods are doing. So basically the basic setup is that we have a smeared histogram, which is Poisson distributed, and its mean is given by k lambda, where in this notation by k, I mean the response matrix, and lambda is the true histogram. And basically the goal then is to take these Poisson distributed event counts and make inferences about lambda. So this looks like a very simple Poisson regression problem, but in practice it's not that simple at all, and the reason for this is that this k tends to be an ill-conditioned matrix, which makes things difficult. And so there are many different ways of actually addressing that problem. Some of the kind of more common ways are listed here on the slide. So there are kind of two kind of generally widely used approaches, and then there are various variants of these two basic ideas. But a lot of the unfolding methods, many of those methods that were, for example, mentioned in Tim's talk, basically boil down to one of these two approaches. So the first one is what statisticians would probably call Tikhonov regularization or ridge regression. In Heinze physics, this goes by the names of SVD unfolding or T-unfold. And what all these methods basically do is that you minimize this kind of a cost function that has a kind of a chi-square type of a data fit term, and then a penalty term, which is trying to kind of encourage physically plausible, less oscillating solutions. And depending on which method you use, this penalty term might look slightly different. I've given two kind of common choices here in the middle of the slide. The one on the left is actually the one that is inside of the SVD unfolding method. So even though SVD goes by the name of singular value decomposition, what it really does is that it actually does this kind of a Tikhonov regularization type of an approach with a certain penalty term. And then the one on the right, the second penalty type of a penalty term, is one that is implemented inside of the unfold. The main point of these both penalty terms is that they basically create a bias towards a some kind of a a priori guess, which typically tends to be a Monte Carlo spectrum. So I've called this lambda MC here. So basically the way the problem is regularized is that you have some kind of an a priori ansatz guess of what the truth should be, and then you create some kind of a bias towards it, and then the details depend exactly how you pick the regularization, the penalty term. Yeah, so that's the first approach, the picking of regularizations. And then approach number 2 is what statisticians would call expectation maximization iteration. But in hydrogen physics, it might be called D'Agostini iteration or even Bayesian unfolding, as we saw earlier in this meeting. And I will come back to that point in just a second. But basically what this approach does is that it's this iterative procedure which it basically starts from, again, some a priori guess, which typically tends to be the Monte Carlo spectrum. And then it tries to kind of in some sense fit that to the data, and you actually have to stop this iteration before it converges, because it tends to kind of blow up at the point of convergence, and this actually happens because it converges to an unbiased solution, and in that kind of ill-posed problems it basically should blow up, and that's what it actually does. And in both of these approaches, it's important to notice that there is the kind of the important question that you have to address, which is the question of the strength of the regularization. So in the case of the Tikhonov type of methods, it's this parameter delta that basically controls the relative weight of the data fit term and the penalty term, and you have to choose this parameter somehow. And in D'Agostini, it's basically the number of iterations you take. So if you take very few iterations, you're biasing yourself heavily towards the a priori guess, the Monte Carlo spectrum, and if you iterate, up to a very large number of iterations, then you start to be less biased, but the variance blows up. And in each case, the answer quantification then is done using error propagation or some variance of that, but potentially using toys and such things. But basically, they're all trying to find somehow the standard error of the unfolded point estimator. So, I mean, there's a lot of things I could say more about these methods, but unfortunately, I don't really have the time in this talk. So I kind of hope that, most of you kind of at least have a rough idea of how these current methods work. And instead, what I will do is that I will give a list of different things that I would really like to see in future unfolding software. So the first point here is actually a very easy one, because it doesn't really require changing the software too much. It just requires changing the documentation, the naming conventions. And the point here is that we really should stop calling D'Agostini iteration Bayesian unfolding. And the reason for this is that it has nothing to do with Bayesian inference. Actually, in fact, what the method does is that it actually converges to the frequentist maximum likelihood estimator in the limit of an infinite number of iterations. So basically, so what this method, okay, and the reason it does this is that it's what statisticians call the EM iteration, and that's a class of techniques that are basically trying to find the maximum likelihood estimators in an iterative way. I mean, it's slightly more complicated than that, because you stop the iteration before it converges. So somehow it's an iteration of finding the maximum likelihood estimator, which you then kind of stop before it converges, and that's what regularizes the problem. But again, it has nothing to do with the way statisticians think of Bayesian inference, and calling it Bayesian just gives a very misleading picture of what the method does. So I think it's fine to call it D'Agostini iteration, even though that's a little bit tricky as well, because D'Agostini was definitely not the first one to propose this approach. I would definitely prefer calling it the EM iteration. So anybody who works on statistics or machine learning would immediately recognize what the EM iteration is, and I think it gives kind of a realistic picture of what the method actually is trying to do. Okay, so that was point number 1. Point number 2 is that I think it's very important that we do not provide any software defaults for the regularization strength. And the reason for this is that, I mean, making this choice is highly non-trivial and it's highly problem-dependent, and there's just no one single universal value that will always work well. And if there is a default, then there's this big danger that analysts will just go with the default without ever really studying, the effect that that parameter plays on the solution. And there's a lot of evidence of that, because if you look at LHC papers that use D'Agostini, there's a huge amount of them that take 4 iterations, and that 4 happens to be the default in RooUnfold. So unfortunately, people just take the default and just go with it without ever really studying. I guess even without realizing that, that makes a huge difference in the solutions. So what instead should be done is to use some kind of an objective criterion that is either data-driven or based on some Monte Carlo studies. But definitely it should be well documented how that choice was made. It should not be done relying on some arbitrary defaults. It should really be based on some kind of a scientific criterion. And that brings us to point number 3, which is that the software should provide implementations of the standard techniques for making the choice of the regularization strength. And I will talk more about this in the kind of the second half of the talk. So we will come back to that point. So another thing I would really like to see is kind of having a full freedom to play around with the regularization and basically, the starting point in D'Agostini and the regularization term and the penalty term in the case of Tikhonov. And the reason this is an issue is that RooUnfold basically defines this bias vector, the one that I've been calling lambda MC, defines it using the same Monte Carlo that was used to construct the response matrix. And so when that happens, it becomes impossible to kind of distinguish the kind of the Monte Carlo effects in the response matrix from the Monte Carlo effects in the penalty term or in the regularization itself. And the Monte Carlo affects the way these methods are set up. It affects both the regularization and it affects the response matrix. And these are highly very different effects and should be studied separately. So I think it's very important to have software that allows you to set the regularization term completely independent of the way the response matrix is chosen. And in fact, that will also enable using kind of Monte Carlo independent regularization. So for example, setting the kind of the bias vector to, let's say a uniform spectrum, for example, which there's well, in certain cases that probably, actually, I guess quite generally I would prefer doing that instead of the Monte Carlo based regularization. So if there is this freedom in the software, then people can study this case by case and see how these different approaches work in the problem that they're trying to solve. Another thing, and this goes very much to the kind of the direction of the previous talk, which is that I would like to see tools that help the analysts do kind of the right cross checks for the unfolded solutions. And the problem is that it's incredibly easy to do circular checks using the current software. And I think that was actually very nicely explained in the previous talk, but let me just kind of reiterate here. So the problem is that, let's say we have 2 different Monte Carlo truths, Monte Carlo 1 and Monte Carlo 2. And the point here is that these are from 2 different kind of Monte Carlo models or generators. So these are not different realizations of the same Monte Carlo model. These are entirely 2 different Monte Carlo models. And let's say that the first one of them defines the regularization. Now, it's kind of it's almost a kind of a trivial statement that now if you check the coverage, you can do various types of checks. The ones that I'm especially kind of advocating here is to verify the coverage of the unfolded uncertainties. So if you check the coverage against the same Monte Carlo model that was used to define the regularization, you will always find perfect coverage. Irrespective of what regularization strength you use. So you can actually, even create a, extremely strong bias with very, very, very little uncertainty, and you will still find perfect coverage. But that's, of course, only correct if that lambda MC1 was the actual physical truth up to the kind of the last decimal point, which it never is. And it's just, that kind of a check gives a completely unrealistic picture of what is going on. And unfortunately, I've seen this happen many times that people become very confused, and I fully understand that it's very easy to fool yourself with this kind of checks. so a lot more realistic check would be to check the coverage against a different Monte Carlo model, and that basically simulates the situation that if you define your regularization using a Monte Carlo model that is it's kind of close to the physical truth but not exactly the physical truth. So what would be the coverage in that case? And I think the software really should support doing this because people get this wrong all the time. And then a couple of further points, and these last 2 points are kind of mostly relevant for the Tikhonov type of methods. So one thing I would really like to see is basically replacing the chi-square term by the actual Poisson log likelihood. So the chi-square is basically just a Gaussian approximation of the actual Poisson likelihood. So what could be implemented in the software is what statisticians would call penalized maximum likelihood, meaning basically that you find the maximum likelihood solution, except that you also want at the same time to have a small penalty term. So basically you need to solve the kind of the optimization problem that's shown here on the slides. And that's actually, I mean, it's not a very difficult optimization problem to solve. So basically any numerical optimization package should be able to do that. And there are even specialized algorithms for this case if needed. But I think this should work quite well with any kind of standard optimization package. And the reason this might be helpful is that if you have very little data, then the kind of the Gaussian approximation breaks down, and it becomes kind of useful to take the Poisson structure properly into account. And finally, I think it would be great to have in the software the possibility of enforcing the positivity constraint. So naturally, bean counts cannot be negative, and if that's enforced, that actually is a completely physics-driven kind of boost for the regularization, because it kind of rules out a lot of unphysical oscillating solutions. So it actually really helps to have that positivity constraint. And again, in this kind of optimization type of approaches, it just means optimizing over the positive real line instead of the whole real line. And it should not be too much more difficult in terms of the implementation. I guess one thing to note here is that actually D'Agostini is based on the full Poisson likelihood, and it does enforce the positivity constraint. But that should not be seen as an endorsement of D'Agostini, because I really find the kind of regularization in D'Agostini to be very ad hoc. It just you have an iteration that you stop arbitrarily before it converges. So what does that really mean? Instead, in the Tikhonov type of methods, the regularization is very transparent. That you have this penalty term that you're trying to put in there to enforce what what your upper beliefs are of like physically relevant spectra in terms of smoothness and other properties. So I find that a lot more kind of transparent and easy to understand. So I definitely personally prefer this Tikhonov type of approaches. Right. So now I want to use the rest of the talk to basically talk about the regularization strength. And I realize that so I guess we are running late. So if you want to cut me off at some point, just feel free to do that. But I will just go on until someone tells me to stop. Okay. So the choice of the regularization strength is a very important point. I mean, it really affects the solution very strongly. And so in the two methods I've described, it's either the parameter delta or the number of iterations that controls the regularization strength. So one way to choose this is to use Monte Carlo studies, and that's to some extent, I guess that's okay. But the problem is that it creates a dependence of the Monte Carlo model, and I think we should try to avoid that. So the way to do that is that you instead use the data to figure out how much you should regularize. And that's a very standard statistical problem, and there's a huge amount of techniques out there for doing that. I've given here a partial list. Unfortunately, RooUnfold doesn't implement any of these. Tikhonov implements what's called the L curve, and then Stefan Smith has his own proposal. Actually, I think this goes back to Volker Blobber originally. So there's this correlation, minimization of a global correlation coefficient method, which is not something that I've seen in the statistics literature. But anyways, it's one method among the others. I think all of these methods should be implemented because that would really help, like, doing proper comparisons of these different approaches in real unfolding analysis. If everybody has to implement these themselves, it's just never going to be kind of proper comparisons between the methods. Now, a very important note here, though, is to realize that all of these methods are designed for doing point estimation, which doesn't necessarily mean that they give you optimal uncertainties. And that actually goes back to kind of my own research. So that was one of the main points in my PhD work, was to, that was one of the main findings there, was to realize that doing optimal point estimation is definitely not the same as doing optimal uncertainty quantification. And the methods that are shown in this slide actually might give you uncertainties that are, badly underestimating the true uncertainty. And here in this slide is the demonstration of that. So I'm showing here the coverage of the unfolded uncertainties from the kind of the two main approaches, so the SVD variant of Tikhonov and the D'Agostini iteration. And I show this coverage as a function of the regularization strength. And what we see here is that the coverage of the uncertainties depends hugely on the amount of regularization you apply. So basically, if you regularize very little, then there's very little of bias, and you have proper coverage of the uncertainties. If you regularize very heavily, then basically what happens is that you're trading variance for bias. So you're introducing a sizable bias towards the Monte Carlo prediction, and at the same time you're shrink your uncertainties, and the end result of that is that those uncertainties are just badly off. They're completely kind of underestimating the true uncertainty because they're ignoring the bias component that you've introduced with the regularization. And the problem is that if we use some of these standard methods, like the cross-validation, you actually end up being in the part of these curves where you actually have real problems with coverage. So basically, if you use one of these methods that are optimizing the point estimation performance, you actually end up underestimating the actual uncertainty. And an important point to note here is that this problem is especially bad when the bias vector, this lambda MCA vector, is close to the physical truth, because that's a situation where the algorithm is very confused about what's really going on, because you're giving it this strong prior that you have this Monte Carlo spectrum which looks kind of very similar to the data, but it's not really the truth, and then you're telling the algorithm to figure out, well, how close to that that prior I should go, and it just ends up creating too much bias. And that's kind of relevant because most of the time in these real analyses, that's exactly the situation, that the kind of the Monte Carlo spectrum is relatively close to the truth, and I'm kind of very worried that there might be like a real issue there. There are some preliminary studies I've done that seem to indicate that some of the other choices of this lambda MCA vector, like a uniform spectrum, might actually work better in terms of the uncertainties, but that's definitely not a perfect solution either. What I hope is a better solution is some of the techniques I introduced in my PhD work, so I don't have time to explain all of them here, but I will explain kind of the simplest one, which is what I call undersmoothing. And that's based on the kind of the simple idea that, okay, so if the standard methods, if they regularize too strongly from the perspective of the uncertainties, then possibly a better way to quantify the uncertainty is to regularize less. So basically to tune the bias variance trade-off to the direction of less bias and more variance, and hope that gives you better uncertainties. And that's actually an idea that has appeared in the statistics literature, but there hasn't really been kind of previous work on how you do this in practice. So one thing I did is to introduce a way of basically choosing how much you should undersmooth in a data-driven way, so that you optimize the coverage of the uncertainties. And the basic idea of the algorithm is that you start with some kind of a pilot estimate of the regularization strength, which can come from any of your standard methods like cross-validation, L-curve, and notch techniques. So any of these techniques that are trying to optimize the point estimation performance. And those techniques typically regularize too heavily from the perspective of the uncertainty. So what you need to do is that you start to regularize less. So you start to reduce the regularization strength. And when you do that, you always check how much coverage you think you have using kind of a plug-in estimate of the coverage. And you stop reducing your regularization at the point where you believe that you're close to the nominal coverage. So you know you're within some epsilon tolerance of the nominal coverage. So let's say you know you have your plus minus 1 standard deviation intervals. So you stop undersmoothing at the point where you believe, for example, that you have 67% coverage with those intervals. And I guess an important point to note here is that the only way to get actual nominal coverage is to not have any bias, which means no regularization at all, which means that things just completely blow up. So that's not really an option either. So you know the point here is to try to find some kind of a nice kind of trade-off where you're able to get good coverage performance, but still kind of avoid the interval length completely blowing up. There's a bunch of kind of details that I don't have time to go into here, but you can have a look at kind of the reference that I've given here for some of the kind of the intricate details. But the point is that it can be done in practice, and in fact it now can also be done in Root. So over the past year, I've been working with a student, Lyle Kim, to implement this stuff as an extension of the Unfold. And we put that code on GitHub, so here's the link, and you can have a look if you're interested. It basically extends the Unfold by introducing 2 new functions. The main function is undersmooth tau. It's called undersmooth tau. So tau is how the Unfold calls the regularization parameter. So it's basically just the square root of what I've been calling delta. And so what this undersmooth tau function does is that you give it as an input your pilot estimate of tau, which can come from L-curve or some other method, and you give it the tolerance epsilon, and then it's trying to figure out how much you need to undersmooth the tau so that you get 68% minus epsilon coverage of the intervals. And the nice thing is that if you already are using the Unfold, then trying this out just requires adding 1 more call to this undersmooth tau. So it's actually really easy for you to try out if you're interested. So I will basically finish by showing how this works in practice. So here's a demonstration. This actually comes from the root code. So here on the left, so this is kind of a simple toy unfolding example. I haven't showed here the kind of the smear spectrum, but this is actually an unfolding situation. So it's a very kind of ill-posed and difficult problem to solve. I'm just showing the same things in the true space. So on the left-hand side is the solution that comes out from if you use L-curve, which is one of the methods implemented inside of the Unfold for choosing the regularization strength. In those figures, the magenta is the truth from which the data comes from, and the black histogram is the unfolded solution with uncertainties. So on the left is the L-curve solution. On the right is the solution from undersmoothing. Now. So in this parallel case, the undersmoothing algorithm picked a value of tau that is an order of magnitude less than what L-curve chose, and as a result, you see that you have wider error bars. And now, I mean, this happens for a good reason, because in fact the error bars on the left picture are badly underestimated, and you can even see somehow in the peak, in the areas with the peaks, you see that clearly there is a bias going on that you don't seem to have kind of good agreement with the truth. And we can verify that by doing a coverage study. So here on the next slide, we have the empirical coverage of those uncertainties that were shown on the previous pictures. And what we see is that if you run the L-curve, the uncertainties that we get out of it just undercover very, very badly. They basically underestimate true uncertainty. While the undersmoothed uncertainties, which were here calibrated to have 67% coverage, indeed seem to have that 67% coverage. And that was done in a fully data-driven way without, any Monte Carlo or anything like that. And there's plenty of, other evidence that, in various different situations, this approach seems to be working quite nicely and definitely improves upon, what's out there currently. Okay, and so just to wrap up, so there are various different ways that the existing software can be improved. I think the main things are to provide the user the full freedom to play around with the regularization, and to provide ways of picking the regularization strength in a data-driven way. In fact, the Unfold already implements some of these, but not all. The uncertainties are a tricky problem, and the key point there is that if you want to get good uncertainties, you want to regularize less than what is optimal for point estimation. And this can be done in a fully data-driven manner using some of the techniques that I've introduced, and we now have some code for doing that. So I guess for this meeting, one of the big questions is what is then the best way forward, in terms of improving the unfolding software. Should we work on extending existing software? So we definitely have good experience of doing that using the Unfold. So we've already kind of started to extend that a little bit in terms of this undersmoothing. So is that the way to go, or should there be a completely new project from scratch? And if yes, then in what framework should it be? Should it be in Root? Should it be in Python, which I guess is the topic of the next talk, or possibly something else? So I guess these are kind of good points for the discussion that comes later. Anyways, I realize that we are running late, so I don't know if there are questions or if you want to move on to the next speaker.
Well, since we haven't been kicked out of the room yet, and I'm hoping to go through my slides very quickly. I think we have some time in case somebody has really urgent questions. But this was very thorough and gave a lot of insight. So thank you for presenting.
Oh yes, Olaf speaking. Can I say something?
Yes.
Sure. Yeah, I just wanted to mention. I don't know. You guys are organizing this Diana meeting, but I think there's so much information tonight on this unfolding. This looks to me like one would need to organize a 2-day workshop to really have a proper discussion. I'm overwhelmed by this information.
Yeah, I agree. I mean, we had an unfolding workshop some time ago. I think that was listed in Tim's talk. We also may have some follow-ups of these PhiStat and data science for high energy physics workshops. That's an opportunity, and Mikael also gave a somewhat similar talk at a PhiStat for neutrino meeting. So I agree that I think unfolding is something that you could spend quite a bit of time on. The part of the point of this this Diana meeting is sort of to see if this is something that Diana should be investing some time into, and its sort of goals of trying to help out with kind of sustainable software. So we have this blend between understanding the sort of current status of the methods we're using and if we're happy with them, and then also how that ties into the software. So I agree that we could definitely follow up. It seems like, given the interest and the amount of material here, either some sort of workshop or at least some follow-up Diana meetings would be very welcome.
There was a lot of discussion recently about the joint Atlas plus CMS statistics forum on the topic.
Yeah, here's Olaf speaking again. Yeah, we will have a 2 hours meeting on the 30th of November. But I mean, I think alone the information given by Mikael, to really discuss this in detail, one would need half a day, 1 day. I think also at the CMS meeting we will not be able to have a really extensive discussion. It's just too short.
Yeah, I agree. I think one of the things, what I find a little bit from talking to Mikael and company and some of my, looking on the side, is that a lot of the high energy physics discussions are cast in terms of how high energy physicists talk about unfolding, and I think high energy physicists need to learn a little bit more about what's a very well studied problem outside of high energy physics. Mm-hmm.
Hello, it's Bogdan here. I would have a small comment concerning Mikael's presentation. So, concerning these data-driven methods for evaluating the bias, if you are interested, I think Chris described this a little bit, but we have some references. I think we started using this kind of methods since 2011 or so. So, if you are interested, I can point you to this.
Yeah, that would be great. Like, I guess so one of the problems that I think there has been very little dialogue between CMS and Atlas. So I've certainly done quite a lot of effort inside of CMS to try to kind of propagate some of the good practices inside of CMS. But I realize that there's a whole new world outside of inside of Atlas, I guess, and I'm sure that inside of Atlas people have come up with different solutions. And kind of it even seems that maybe some of the kind of the techniques that are used are quite different inside of Atlas. So yeah, so any information of what's going on inside of Atlas, I would be very happy to learn about that. And in general, like any of these resources that I'm not familiar with, I'm very curious to learn more about. Definitely.
Okay, then it's fine. Probably we can discuss this at the meeting between Atlas and CMS. Yeah, okay.
So this is Louis here. Can I just ask Mikael? I don't think you said anything about unbinned unfolding. You're working on that still?
Right. So yeah, I guess it depends what you actually mean by unbinned unfolding, but there is, I guess there's various things that can be called unbinned unfolding. One of them is to use a different set of basis functions than histograms. So to use things like splines, and I think Igor briefly pointed out about that it's in some sense the more natural basis system is to use something like splines or something else. That's one thing.
Polynomials.
Right. Yeah. I mean that's another option. Then there's the kind of, so that's in the kind of the unfolded space. Then there's the space of the observations. There's another set of binning. In some sense, that's an easier situation because by binning that space, it's only a loss of information, but you don't really create biases by doing that. So I think that's lesser of an issue. It's so I guess the main effort on unbinned unfolding should be kind of in the unfolded space. And actually, I mean, a lot of my own studies I've done using splines. So all that stuff that I've done, I mean, most of the stuff I've done in my PhD thesis, they're using splines. So that's one way of doing unbinned unfold. Actually, I remember that we talked with Kyle about using Gaussian processes, which is, I mean, it's almost the same as building some kind of a basis system on the unfolded space. So that's another way of doing unbinned unfolding. To put some kind of a Gaussian process prior on the unknown function. So that's another way of doing that.
Yeah, it's interesting that Louis mentioned that because, in my point of view, binning is not necessarily should be the part of what we're doing when we perform unfolding, and eventually, I hope we will be able to represent the unfolded data in such a way that we don't explicitly regularize it. So my hope to leave the regularization to the people who will try to analyze their model based on the unfolded data rather than to perform it ourselves.
You could just give them the folding matrix and the data then.
The problem with doing that is that it's not just the unfolding matrix that you want to give. It's also all kinds of systematic uncertainties, and there is no standard for that, right? So, but if you can give them, for example, an expansion in terms of statistically independent orthogonal polynomials as the result of your unfolding, then you're kind of done, right? So, your uncertainty is going to blow up with n, and somebody will later decide what kind of n they're going to use.
Yeah, that goes kind of back to the old discussion of whether you should unfold or fold, and that's a long, I guess, endless discussion. But I kind of like what Igor is saying, that maybe we need to find different ways of representing the unfolded space. And there was this interesting talk by Volker Global quite recently. I think he estimated like moments or something like that in the unfolded space.
Yeah, it was Chebyshev polynomials, but my complaint about that Chebyshev polynomials are in no way optimized. It's not an optimized basis. We need a better basis.
Right. I mean, I guess the way I would like to think about it is to say that, okay, we have the unfolded function, and we want to extract some kind of functionals of that, and those functionals can be bins, they can be moments, they can be something else, and try to kind of find ways to estimate, kind of the appropriate functionals in a rigorous way and get the uncertainties in a rigorous way. But that's tricky.
Mikael, you actually don't want to regularize. Instead of regularizing, you want to determine those functional with the complete uncertainty. And then you let people decide which functionals they're going to use to fit their models.
Yes, correct. Like I mean, like and you probably know very well this paper I wrote with Philip Stark, and that it's basically has this kind of idea that you have the unknown function, you're extracting functionals of that, you provide rigorous uncertainties for those functionals. So I would kind of like to have that framework, but try to improve upon what we did by kind of reducing the over coverage of what the what the method we proposed has. I think there are ways to do that, and I think that's kind of the right way to think about it. Is that you have, you ask the analyst to choose what are the functionals you care about, and then you provide an algorithm that gives you rigorous confidence intervals on those functionals.
Why do you want regularized one? Give them unregularized.
No, not regular. I didn't say regularized. I said rigorous.
Sorry, can I
rigorous.
Briefly?
Okay.
I think we should let Vince give his talk.
Yeah. I was about to say we should bring this to a close. This is very valid, very interesting discussion. But yeah, I mean, you've also brought up some of the topics that I had in reserve for the discussion if we had time left over. So perhaps we bring this to and also look forward to the next discussion when we can bring all these back up again. Is there any last points, parting shots somebody wants to mention, or shall I just start? Okay, I'll go. So I very quickly, just over a month ago, I started. I started a project which is to port over the RooUnfold implementation into Python. This might be useful for two different cases. Either you want to use this in a case where you have a system which doesn't have root involved, whether you're doing some other kind of root independent system, or you want to be able to use the response matrix and do your own sort of studies. But it's also useful because, of course, this problem isn't a HEP-specific problem. This has been used throughout signal processing and imagery and geophysics and all sorts of things. So it might be useful to have a Python-specific implementation such that we can compare the algorithms that we have with industry standards and things like this. I got an email 9 p.m. last night saying that actually somebody's already gone and done this with a single algorithm, which is the fully Bayesian unfolding. There's a link to an archive paper explaining this algorithm, and basically they've implemented a similar sort of thing. There's a response matrix and various implementations. It depends only on NumPy and then PyMC for the Monte Carlo sampling. And apparently this has already been used in several top quark measurements and is similar to what I've started, but a lot more mature, obviously. So these sort of things are already implemented, and there is actually a need for them. So people are actually using these things, and it's very easy to download and install and start trying out. What I also found is looking at all of the various implementations that are involved outside of high energy physics to solve this generalized problem. And indeed, as Mikael went into a lot more detail in the last presentation, a lot of these problems is dealing with these large ill-conditioned matrices and linear systems, where it's either the matrices are not full rank or whatever, which in our case means that there's lots of bin-by-bin migrations and things like this. Yeah, I'm just going to point out three of them. There's some of them that are specifically for Bayesian inversion. There's some that use different ones that seem to be more geared towards the image processing, and another one that is an iterative Tikhonov implementation of these things. So this just merges the two implementations that Mikael was talking about. And none of these work out of the box on the histograms that we're used to dealing with in high energy physics. So yeah, at this juncture, towards the beginning of these sorts of studies, it's trying to work out what actually we want from the next round of software for high energy physics, because of course RooUnfold already has a Python implementation and it's fairly easy to install. But do we want things to be up to date with one general core repository of things? Do we want lots of different algorithms to be able to implement it? Or do we want to actually really check that the algorithms that are being implemented by this different software are actually being implemented correctly? They're not just using default values for the regularization strength or things like this, and people are actually understanding what's going on. All of the other implementations outside of unfolding that I've seen for this problem are fairly specific to different cases, and these have to be taken into account, and whether or not we can build some checks in order to verify that the different algorithms are being applied in the right way. And then there's this other case is unfolding seems to be specific to histograms. It's histogram unfolding, which of course is great for us. This is how our measurements are usually performed. It's how we deal with our Monte Carlo. It means that, for instance, in different software, we can just use a two-dimensional histogram as our response matrix, or n-dimensional histogram. But this introduces a whole host of new issues, which we went into a long discussion about just now. So, yeah, this is a brief overview of the issues faced for if we want to be developing a new generation of high-energy physics unfolding software. But yeah, I also hope for some discussions. Which we possibly might have to take offline because we've gone 40 minutes over time now, and I'm sure a lot of people are wanting to get home. Are there any comments, or how should we proceed with discussions on this? Of course, there's lots of people with lots of different views and opinions on these sorts of things, and it might be appropriate to start an actual forum or schedule another meeting.
Yeah, I guess it would be good to have some kind of an email list or a news group or something, right? Because I mean, if something should be coming out of this, it would probably be some kind of an approximation to a standard, right? So hopefully, and to define a standard, one need quite a bit of discussions.
Yeah, I agree. I mean, one thing I think would be interesting is, for instance, looking at something like the interface for RooUnfold and forgetting about the implementation and just see if we're happy with the interface for it. But certainly if you want to move away from histograms and start moving into basis functions and things, it doesn't seem like that's possible. So somehow I think if we're talking about a new software effort, some kind of list of requirements that would then start to be the basis for some kind of standard would be good. Maybe what would also be good is to let during this Atlas CMS meeting, to try to reserve some fraction of time for this kind of aspect of the discussion. So it's not just a shootout of whose method's better and things like that, but that we have we think a little bit forward about the software and see if we can identify the shortcomings of what we have and what things we would like to have addressed, and then that can be in some sense a a community roadmap of the software for unfolding.
Yeah, in a sense, we need also to consider use cases and the presentation of results so that it could be conveniently used by people who would try to fit the physics models to what we provide.
Yeah, I especially liked Chris's suggestion of, or his started work on a set of standard results for comparing different algorithms, and it would be very useful to have a set of problems and a set of standard data that is public between various experiments that can be used for these sorts of checks.
Well, I think even before that is defining, what are the good figures of merit? What are the ways that you can say whether you've chosen the best the best regularization parameter, the best algorithm, or the one that works well? And like the list that Mikael was showing of all the different methods of these choices, we need to kind of define some standard methods. And I was hoping that Chris, and he sort of mentioned this at the end, that that this could be actually encapsulated in some package. It doesn't. I think at this stage the API of that package is less important than having something, and then we can work on making something that's easy to use. But the first thing is to actually define something.
Yeah, but please be careful not to compare bins to bins, because as I said, in this case, one bin unfolding will always be the best.
This is Olaf one more time speaking. Yes, I mean, it will happen 2 weeks this meeting, Atlas CMS, but I think it will be probably in a way as limited as this meeting is now because of time. And but I mean, we had some agreement with Glenn Cohen and George Redlinger and so on, that maybe eventually we could have some workshop between Atlas and CMS, and unfolding could be one of the topics. I think we cannot really discuss this in 2 hours. We can make some list of topics and problems, but within 2 hours it's impossible to have a really extensive discussion.
Yeah, I agree with that. I think, Olaf, what's your reaction to this comment that I was making, that it would be nice to reserve some small fraction of time just to discuss a little bit about planning for potential software developments, which would be a longer term project, but just to start some kind of planning or discussion around that.
Hello.
Okay, Olaf, I was asking if you had any reaction to that.
I'm sorry, I didn't get the question. What was the question?
Do you think it would be possible to reserve some small fraction of time in that meeting to initiate the discussion of the sort of community software aspects of what's
Yeah, of course.
Yeah.
Yes, of course. I mean, for instance, now I think Stefan Schmidt is also connected. I don't know if you, Stefan, could you comment on this? Maybe muted. No, but definitely, my answer is yes.
Okay, great. Thank you. Yeah, I mean, certainly we're not going to get to the bottom of anything, but I think it would be nice to, I could see very easily that all of the time goes into issues about, this method and that method, and without getting kind of any time to discuss the sort of future planning for potential, software and wish lists and benchmarks and all these things.
But exactly, this was a bit confusing for me tonight. I mean, I thought you would discuss more software, but finally, it seems to me we just opened up the discussion on the issue, the unfolding. So for me on the software, I thought it would be more focused on that actually.
Yeah, well, I tried. It's hard to get physicists not to stay on topic sometimes.
The sense are interconnected, Olaf, because there are many issues, and to deal with those issues, you probably cannot create like a top-down software design, right? Because you don't even know to begin with what problems you have to solve.
There's a question.
Can you hear me?
Can you hear?
Hello.
Yes.
Okay. Thank you. So Olaf, this is Klaus speaking. So in fact, there are 2 questions, and one that was raised is which software framework to use, and this is completely disconnected from the question of which are the best or the right algorithms. So there are 2 questions to address, and in terms of software frameworks, I definitely think that there could be multiple possibilities. So for example, having Python versus Root versus something else is perfectly nice to have several versions if people want to support it. In terms of the algorithms, then we need a discussion on the setup of test what is the best one in certain cases. So we should reserve discussion on both.
Yeah, absolutely. So, but
I mean, I would like to avoid a little bit the discussion about kind of framework in the sense of Root and Python. It's pretty narrow. I mean, I think there's an issue before that, which is more in terms of what do you want the methods to be able to do, without getting into the details of how the methods work, but more in terms of, for instance, are they going to be restricted to histograms or not? Yes or no, right? That's going to influence the design of the software. and looking at the software that we have now, does anything satisfy that, yes or no? And is that something we would like to have, yes or no? So it's something which is informing what the software design would look like without being so specific as to, like if it's C++ or root or something like that, but more a review of, features that you would like and interface issues and things like that. And then once we can sort of get a feel for what we would like and where we stand currently, then we can start trying to organize a potential kind of longer-term community software effort.
I think that the point that Vince made about kind of having some test cases available is a very important point. I mean, that's a point that almost always comes up in these unfolding meetings, but then nothing really seems to happen. Like people, people always bring up this point. I think it would be extremely important to have like real-world, LHC physics, cases as kind of unfolding case studies. Because right now we are doing this with these kind of like toy examples. Like, I had this like, two-picked example, and also Tim had this two-picked example, which, everybody always kind of points out that, but, usually we don't really have, they're not really unfolding peaks. So it would be great to really have these, realistic test cases, to serve as kind of, to support the kind of the method development. And I think that would really require some effort from the kind of the physics side and the analysis side, because it's not, it's not something that, for example, I cannot do that. I cannot create those data sets, but I can work on creating methods if someone creates those data sets. So I think that's an extremely important kind of point to try to, actually create those test cases.
I think that's a bit, I guess Chris's talk demonstrated this, that there's a problem if you want to show real data, that usually this data, particularly if you're looking at the original distributions, it may well be internal, or is often internal to the collaboration. So it's great for a collaboration discussion, but then when you have a discussion between Atlas and CMS, it then becomes more difficult. And
yeah, but I think we can generate fake data that's realistic looking, and also in the context of the machine learning discussions in Atlas, we were talking about making simulated data sets available, so you can have Monte Carlo truth and fully simulated Atlas data and things like this. So I think we can get around that without, without it being like actual real data.
And similarly for CMS, there's the open data that doesn't have this issue. So in principle, those test cases can be generated using the open data.
Yeah, the reason I think that we've not done it, at least in Atlas, is that people have wanted to do these comparisons, but of course they want to do it on the analysis they're actually doing. So you need somebody who's got the time to develop one of these externally. And I agree, if somebody can generate one of these, generate some of these samples independently of the particular analysis that they happen to be working on, then we can make progress.
Maybe this is useful when developing new methods, but on the experimental side, actually, when an analysis is done, if we perform data-driven tests, this is not so relevant anymore. I mean, the decision on which method performs best can be taken at that level, at the analysis level, where everything is available.
Yeah, but then if you have a set of open data examples, you can say, look, these are the sorts of tests you do, and then when you move to your analysis, then you perform these tests on your analysis, and it encourages people to actually take all of these things into account, rather than just using the default for their analysis, or the one that gives them the best result.
Yeah, but I mean, the test, you can show them also on pseudo data.
Yeah.
Yeah, I think, well, okay, I'm repeating myself here. I think the important thing is to develop, make it easy for people to do the correct thing, rather than rather than give them very complicated instructions. So having a standard framework to do the correct thing helps. And I think that's what we're talking about for developing. It's not just developing the perfect unfolding algorithm, it's developing the perfect, or the way to make it easy for people to do the right thing in choosing between algorithms and choosing between regularization parameters and so on.
Right. Can I throw up one other aspect of this, which hasn't come up but explicitly, but kind of was there implicitly? So Igor was, for instance, talking about how this ties into how we share the results, right? If we imagine some kind of potentially drastically different way of doing unfolding from the way that we've been doing it, then you know, a lot of the considerations and a lot of the reason we do unfolding in the first place is largely about making it easier to communicate between the experimentalists and the theorists and things like that. So, you know, one aspect of this discussion we should keep in mind is, for instance, if we have a new unfolding framework, if it talks to HEP data directly and things like that, if there's a way that we can improve or standardize the way that the data gets, like the results get uploaded into HEP data or something along those lines. So, you know, that starts moving into very much the kind of practical aspects about how the field uses unfolding and not just focusing explicitly on like who's the best unfolding algorithm.
Yeah, so I think if there's going to be a big unfolding workshop at some point, it would be very important to invite some theorists there who actually, you know, use these unfolded results to give feedback on, you know, what do they expect and what do they want to have, and, you know, what kind of things can they, you know, use as an input to whatever they want to do. So yeah, I think it would be very important to bring into one room people who, you know, who actually do the analysis, one set of people, then another set of people who develop these methods, and then a third set of people who are actually the consumers of the unfolded results, so typically the theorists.
Yeah, I agree. Okay, well, great. Well, I'm going to have to sign off soon. We've gone a bit over. But it looks like we have quite a bit of interest in this topic, and maybe we should try to organize something sooner than later. Okay. Any other departing comments? No? Okay. Well, thank you to our speakers, and have a good evening, everyone.
Bye.
Thank you. Bye-bye.